Welcome. Today we're going to be taking a look at the notes worksheet entitled Simple Harmonic Motion. And as it says on your paper, the periodic nature of trigonometric functions is useful for describing the motion of a point on an object that either vibrates, oscillates, rotates, or is moved by wave motion. And so what this will end up being, everyone, is an application of sinusoidal modeling. And so what we're going to do is take a look at an investigation that's on your paper there. Looks like I pasted a little diagram in to make it a little more visual for us. And let's give it a try. We'll see if we can fill in some good ideas. So it says, consider a ball that is bobbing up and down on the end of a spring. Suppose that 10 centimeters is what's called the maximum distance that the ball moves vertically upward or downward from its equilibrium. So essentially this is going to be what's called our displacement. And it's going to either move up or down from the rest position. Also, suppose that the time it takes for the ball to move from its max displacement above zero to its max displacement below zero and back again, and that should ring true for us as the period, is 4 seconds. Assuming the ideal conditions of perfect elasticity and no friction, the ball would continue to move up and down in a uniform manner. Okay, so we have a little diagram right here. Here is the object at the rest position, and this little spot right here would be the object at the maximum negative displacement, so 10 centimeters below the rest position. And then this part of the diagram right over here would represent the object being 10 centimeters above the rest position. And so what we're going to do is just sort of model the motion of an object just like this. And what we should see is it matches some of the sinusoidal functions that we've been developing in this unit. Okay, now I'm going to go to my next board here, and we'll go ahead and fill in some pieces. So it says, first and foremost, period is the time that it takes for one complete cycle. And so think about that description from the investigation and see what number we're going to put in there. And then here's a good one. We haven't seen this before, but it says frequency is the number of complete cycles per time period. So let's see if we can relate this to the investigation above. And it says on your paper, from this spring, you can conclude that the amplitude is, and so I guess I would ask you to fill in a couple things as we go through here. First and foremost, the amplitude is the distance from the midline to either its max or min, and I'm hoping you would all realize that it is 10 centimeters. So negative displacement is 10 below, and the maximum is, the positive one there is 10 above. So 10 centimeters is going to be our amplitude. Its period is, and let me go back a screen, so this would be setting the stopwatch, and how long would it take to go from rest position down, back up again, and then back to the rest position. So one full cycle, and as it says sort of on your paper here, that would be 4 seconds. All right, so I'm going to fill that in. Its period is definitely 4 seconds. Now comes the quantity that we haven't quite seen before. It's the frequency. So think about this for a moment. If the period is 4 seconds, then how many cycles would it be able to complete in a single second? That's what frequency is, the number of cycles per second. So if I go back one screen here, again, let me just go over the period part of this. So I start my stopwatch, and it goes from starting right now, goes down, up, and back down to here in 4 seconds. So if I start my stopwatch and stop it just after a second, it looks like it's only able to do a quarter of the cycle. And so I guess I would say, and I'm hoping you would agree with me on this, the frequency would be a quarter of a cycle in a second. Okay? 4 seconds per cycle, and so a quarter cycle per second. Now it says on your paper, just to make sure we're really sure about the relationship here, it says what is the numerical relationship between period and frequency, and I'm hoping based on what you see in these numbers here, and if we were to do period and frequency for any values, they should be reciprocals of one another. So one represents how long it takes for a single cycle, so one cycle in 4 seconds, and the other one is a fourth of a cycle per second. So they are reciprocals. Okay, good. As it says on your paper, motion of this nature can be described by a sine or cosine function and is called simple harmonic motion. So essentially an object that moves either back and forth along the same path can be modeled with simple harmonic motion, or an object that moves up or down by the same path can be modeled with simple harmonic motion. So it says on your paper, and we'll underline a couple things and fill some things in, the models for simple harmonic motion are, and actually if you don't mind, let's box this up right here. Just depending on where we start, we're going to either use sine or cosine. So if you can see on your paper, as a matter of fact, it's been a long time, but you can kind of see some of the variables here, especially this. That's what I was peeking at. Remember that lowercase omega from way back when we talked about circular motion? There it is coming up again, as a matter of fact. And that's just another way to talk about the b value. That omega, if you remember correctly, dealt with the angular speed. And as a matter of fact, the angular speed and the b value in our sinusoidal function are identical. And so in this case, we're using the angular speed as a way, and it says right here, as a different way to denote the b value. Essentially, it is just b. Okay, well, let's go for it. T represents, and let's make sure we fill it in, essentially time. So the independent variable, I'm going to write that here as well. And D represents the displacement. And again, we want to be careful, either above or below the rest position or the equilibrium. So fill that in there if you would. And I guess what we want to do is call that the dependent variable. I'll go ahead and fill that piece in on the end. So we have displacement in terms of time. That a value, of course, as we've seen before, nothing dramatically new here, by the way. It's just a very particular way of modeling a sinusoidal function. So a is the amplitude. The period, as it always has been, if you remember, the period is 2 pi over b. In this case, of course, our b value is that omega, that angular speed, so just 2 pi over that. And then I guess since this one is new, let's focus on this piece. The frequency, of course, would just be the reciprocal. So again, if the period takes a certain number of seconds, then it's the reciprocal of that in terms of cycles per second. And so if this is the period, then I guess the argument can be made that this, everybody, would be the frequency. Okay, so from our sinusoidal model, representing simple harmonic motion, those are the pieces that we're going to take a look at. And so what we'll do is just try a few examples with this. Just kind of either creating it or working with it algebraically, and we'll see how that goes. So I'm going to go to my next screen, and let me just read the little blurb that I have above, and then we'll go for example one, right away here. So it says, while this scenario seems contrived, and again, really the big piece here is it assumes there's no friction. And by the way, this is what's called a simple harmonic motion. If we included the friction piece, what you would see, of course, the path of the object would be getting closer and closer and closer to the equilibrium. That model is what is called damped harmonic motion. So anyway, while this scenario seems quite contrived, the models for simple harmonic motion can be applied to a variety of topics, and these topics include radio and television waves, light waves, sound waves, water waves, etc., etc. So again, really the path of an object moving back and forth or up and down on the same path. Okay, well let's start it out here. Just if I give you a model, can you work with it a little bit? And let's see what we're able to accomplish. So I'm going to go ahead and box this up, kind of formulate this piece right here, and I have an A, B, C, and D with it. So number one would be the maximum displacement. So this would be how far above or below equilibrium. And that, again, is just another way to talk about amplitude. So this would be 6 units. And so I'm going to just go ahead and write it like that. Okay, good. So amplitude talks about the displacement above or below the equilibrium. Find the frequency, and it does say include units. So I think we'll have to be a little careful here just in terms of our numbers. But remember how we defined frequency. It's really the reciprocal of the period. So if I asked you for the period, you would tell me 2 pi over this. So let's do this over 2 pi. So everybody, frequency, again, sorry for being redundant here, is the reciprocal of the period. So instead of 2 pi over b, or in this case our omega, it's omega over 2 pi. And I like just kind of doing this piece right here. Again, just from a visual perspective, that works for me. but basically kind of showing you this before, sort of that outside over inside trick. And so if I go ahead and do this piece, I end up getting 3 pi times 1, which is 3 pi, and 4 times 2 pi, everybody, is 8 pi. These should cancel, and I think we've got our number right here. So how many cycles every single time unit? We will assume seconds here. I didn't put it in. So how many cycles per time period? It looks like 3/8 of a cycle. And I'm just going to write it like this since I didn't put it in. But typically it's in seconds. So 3/8 of a cycle every single time period according to this model. And again, if I asked you for the period, you would just flip this. I'm just going to write it off to the side, just kind of thinking out loud. This would be 8/3 in terms of time frames or time periods. That's pretty poorly worded there. But in this case, we'll probably go seconds. I don't like that piece. So that would be 8/3 seconds if we wanted to do a period. Sorry, got off track there for a sec. Okay, well, let's go get C and D. With any trigonometric model, the hope is if I give you an input, you can work with the output, and vice versa, of course. So I'm going to just work below a little bit. In this case, I'm going to go ahead and put in 4 for T. So let's see. And I'm almost thinking we could do this without a calculator. Kind of know some of our stuff by now with some of these numbers. So 3/4 and then times 4. And again, you're more than welcome to pick up the calculator at this point. I'm just going to play it out as best as I can here and then see what happens. But basically, I get 6, and then cosine. These are going to cancel, everybody, and so I get cosine of 3 pi. Now, of course, picture this. Probably gave this to you way back when we talked about unit circle. What actually is the cosine of 3 pi? Well, the cosine of 3 pi, being all the way to the left on that unit circle, should be -1. And so you can see here that the displacement would be -6 as a result. Excellent. So that means it's at its maximum negative displacement at 4 seconds. All right, wonderful. And in letter D, find the least positive value of t for which d equals 0. So what's the first time it hits its rest position? And so everybody, I guess if you would, let's go output to input here. And again, if we need the calculator, we'll pick it up. If we can work through it without, let's do that. I think that's preferable, to be honest. Okay, so let's take a look here. And first and foremost, if I asked you to solve for t, you would probably all divide by 6. And so dividing by 6 just gives us this piece right here. So cosine 3 pi over 4t. Wonderful. Now, of course, I'm probably going to want to undo this cosine right here, take the inverse of both sides. When I take the inverse of the right-hand side, of course, I get this. Now, of course, as we've just sort of talked about this piece before, I think you do know the inverse cosine of 0 as a matter of fact. So this would be the angle between 0 and pi that has a cosine ratio of 0. And that angle, of course, is exactly pi over 2. And remember, if you decided to use a calculator here, you would go ahead and type in inverse cosine of 0, and it'd give you that 1.57 and change there, which of course is pi over 2. Alrighty. Well, let's see. What do you say we either divide by this or maybe multiply by the reciprocal, some version of that. But essentially what you're going to do is 4 over 3 pi times pi over 2. So many different ways to kind of look at that piece. But essentially we're going to have to get rid of that 3 pi over 4. And so this might offer us a good way to do that. And so I'm seeing this piece right here. And I'm getting 4 over 6, which is 2/3. And again, I'm just going to put seconds here. I've been balking on this now, the whole problem. So I'm just going to go 2/3 of a second. And should have obviously put that in the original problem. But that's all right. The math works out quite nicely. Okay, so just working with a simple harmonic motion model. In this case, it used cosine. A lot of it will depend on the starting position, and we'll kind of talk about that hopefully on the next one here. All right, everyone, I'm going to go to my next page, and looks like I have the last 2 examples taken care of. And so example 2 is just to create the model, and then example 3 we'll do, sort of put examples 1 and 2 together. We'll create and then utilize. All right, everyone, well, let's take a look at example 2. A ball on a spring is pulled 6 inches below its rest position and then released. The period for the motion is 2 seconds. Write the equation for the ball's simple harmonic motion. All right, sounds great. So, here's our object right here being pulled down. Here's the rest position. It's being pulled down initially 6 inches below. And then, again, theoretically, it's going to go back and forth, et cetera, et cetera. Now, a couple things to, sort of think about as we go through this. Obviously, guys, we want D equals our displacement. Amplitude, here is my rest position right here. Amplitude would be either from here to here or from here to here. And again, that shouldn't surprise us here that the amplitude is going to be 6. Now, we're going to be a little careful on this because I'm going to modify something in just a second. The question I have for this particular problem is this. Which one should we use and why? So think about that for a sec. Pause the video for a moment and think about where the starting value is and which one are we going to use. Okay, well, what I see, everybody, is we are starting at what I would call the minimum. So all the way down at the bottom, and as a result, it seems like if we're starting at a minimum, we're going to want to use the old flipped cosine function. So we're going to go cosine on this, and as a matter of fact, before I forget, flipped cosine means throwing the negative out in front there. So A can be negative, and in this case, I would certainly encourage us to include it. So starting at the bottom of the path, it looks like flipped cosine to me. And then it's going to go up and down from there, Okay, good. Let's see, we need a B value, of course. And so the B value would be, or the omega value in this particular case is still the same. It is really just 2 pi over the period. And so that is our omega value, so to speak, the quote angular speed. And so I'm getting 6 cosine pi t. And notice there's no vertical shift on this. The midline is going to be 0 because here is your midline right here between a positive 6 and a negative 6. So midline is always going to be 0. And that's why you saw when we created these models initially and we kind of boxed those up, there was nothing on the back end there. There's no phase shift and there's no midline. Well, the midline's 0, I guess. All right, so negative 6 cosine pi t. All right. It would be great if you could try to write the equation for letter A and then go from there. But let me at least read letter A, and then we'll sort of take it in stride. So a buoy oscillates in simple harmonic motion as waves go past. At a given time, it is noted that the buoy moves a total of 2.8 feet from its low point to its high point, and that it returns to its high point every 5 seconds. Write an equation that describes the motion of the buoy if it is at equilibrium moving upward at time 0. So basically, it's going to be at the rest position, which would be in between the positive maximum and the negative maximum displacements. Okay, so I would encourage you to pause the video for a moment and see if you can come up with a model for this. And then come on back, and I'll pause for just a sec, and then I will see how you did, of course. Well, let's see how you did. The first thing I did with this is I kind of just sketched it out here, kind of the buoy at the low point, going up to the buoy at the high point, and what I saw the distance between those two things is 2.8 feet. So I did this piece, and then right smack in the middle there, which again is going to be our equilibrium, and we're going to have that be 0. What that means for us is essentially it's going to be 1.4 feet up and 1.4 feet below. So that's how I'm seeing the simple harmonic motion here. And so the way I kind of put this together, everybody, is that displacement is going to go from that rest position 1.4 feet above it and then 1.4 feet below it. So that was the first order of business there. And then what I did in terms of the period, 2 pi over the period in order to get my omega value. Oh, and by the way, I guess we should talk sine or cosine here before I even do that. Here's the key, I think, with this one, everyone. If it's at equilibrium, and there's a reason I put moving upward, by the way, at times t equals 0. So the initial value seems like right here at the midline, so to speak. Initial value at the midline is definitely sine. The reason I have it moving upward is just to make sure we differentiate between a sine function looking like this would be moving upward, or a sine function looking like this. This would be moving downward. This is your basic sine graph. This is your flipped sine graph. So no flip necessary here. Okay, and I think I had mentioned 2 pi over the period, so 2 pi over 5 times t. Okay, that's great. So that's what I have as my model, and then let's just utilize it with B and C. This one I think we will need the calculator for it, but let's just make sure we're ready to roll. So I have 1.4 sine 2 pi divided by 5 times 24, and that should give it to us. Again, no phase shift, or really the phase shift is 0, midline is 0, and so the only thing we just have to be careful of here is just make sure you're in the right mode, which would be radian mode there, of course. So we're really, again, this is that branch of trigonometry called the trigonometry of real numbers, where we're just going to go ahead and take the sine of whatever this is, not as an angle measure in degrees. Okay, so let's see, 1.4 sine 2 pi divided by 5, and then times 24. Close that on off if you want. And that's what I get. So it looks like we have a displacement of about 1.33 feet, it looks like in this case, below the equilibrium. So I'm going to write it as this right here, and that's looking pretty good. So as a matter of fact, after 24 seconds, sort of close to the bottom there. So this would be 1.4 above, and you don't have to write this, and 1.4 below, with that being the 0. Okay, wonderful. Let's see, letter C. Determine the first value of t for which the location of the buoy is 3/4 of a foot above equilibrium. And just, by the way, just in terms of this piece, we're always finding here the first value. Theoretically, there are an infinite number of values as this goes up and down, up and down, up and down, where the displacement would be 0.75 feet. We're not there just yet in terms of being able to solve that and represent that, but that is definitely sort of in the future for this curriculum. Anyway, let's go for it. 0.75. And I'm going to do 2 pi over 5. And let's see, times t. So I'm hoping you kind of see the 3 steps here. I have a couple of numbers on my paper, so I might just go ahead and utilize them. I'm hoping everybody would be in agreement. We do want to divide by the 1.4 first. And so I'm going to do 0.75 divided by that 1.4. And having already done that, I have this number right here. So sine 2 pi over 5 t. Excellent. And now what I'm going to do is inverse sine, both sides. Inverse sine over here gets rid of it. Inverse sine over here should give us a numerical value. And again, I'm going to bring this on up if that's all right. And so I get about 0.5654, about 4 decimal places out there. We'll rein that in as we get our answer here, but equals 2 pi over 5 t. Then, again, what I would do here is just multiply by the 5 over 2 pi. If you have this number as a decimal, you can just divide it right away. Probably different ways to kind of pull this off. But regardless, if I take this right here and multiply it by 5, and then divide by the entire 2 pi, just make sure you put that in parentheses if you divide by 2 pi, I get about just under half a second, so about 0.45. So check your calculations with what I have going on up here, but I, in essence, get that piece, so about 0.45 seconds. Alrighty, nice. So this is kind of the end of our unit here where we're just dealing with, as we saw yesterday, just a nice little application using right triangles, the bearings, and in here just a nice little application using sinusoidal models, what's called simple harmonic motion. So a good way to kind of round out this unit before really shifting the curriculum and going into the next unit. So please let me know if you have any questions on what you've seen here today. Create the model, utilize the model, should be just fine with it. You have a great background with this at this point. Well, of course, thank you very much for listening. I appreciate it. And just help each other out and make sure you do the practice work.